So this is our group 9. So I'm excited to walk you through the progress we have made on our project in our update 2 presentation. So the real-time weapon detection using computer vision. So this is our second update and we'll be talking about the improvements we made and the result we got and the directions we are heading in. So the revised approach from custom model to YOLO. So in our first version in the update 1, so we built a custom model from scratch using PyTorch. That's a machine learning tool, but the accuracy was little low and we figured out why. Like we had limited data and class imbalance, meaning we had more images without weapons than with weapons. So in this update, we decided to switch to a more powerful model, YOLO V5. YOLO is you only look one. That's the famous model for image detection. So we had chosen version 5 of that. So it's a smaller version of YOLO, which is famous for real-time object detection. And it's fast, efficient, and performs very well even on smaller devices. So as we are doing student projects, so it's very useful for us. So making it a great fit for our needs. And let me move on to the model selection. So we chose YOLO V5SU because it's light and accurate and a good combination for quick real-time detection. So instead of building everything from the scratch again, we fine-tuned this model using our dataset. So the pre-trained nature of YOLO helped us really very better to get good results with limited data that we have. And let me move on to the training and validation. So here you can see our model's training progress during training. It's all like learning progress. The three types of losses: the box losses, classification loss, and DFL loss. So we can see from the image that I attached, it all went down steadily. So which is a sign that model is learning correctly. So not just that, the validation losses, which measure how well the model performs on unseen data, also decreased. So this means our model is not just memorizing, but generalizing very well. And we also tracked metrics like precision, recall, and MAP, that is mean average precision, and those consistently improved across 50 learning efforts. So this shows the model became better and more confident over time. So let me move on to the evaluation of confusion matrix. So I attached the confusion matrix here. So this confusion matrix shows 31 true positives, that is weapon detected correctly, and the 53 false negatives, which is more concerning, but that shows us a weapon that the model missed to detect, and 33 false positives, that is things wrongly identified as weapons. While it's great that we have true positives, the number of false negatives is a little bit concerning, I can say. So this likely happened because of class imbalance and possibly the similarity between background objects and weapons. So while the model is working, we still have to improve its ability to detect all weapons accurately. And let me move on to the F1 score versus confidence threshold. So this shot helped us find the sweet spot for our model's confidence threshold. That is the middle of that, not more, not less. So that's the level at which the model says, like, yes, it is. And let me move on to the slide label and bounding box detection. So this slide tells us something interesting about our data set. So when we looked at the position and size of the bounding boxes, the rectangles around weapons, we saw that here most weapons were in the center of the image. Most bounding boxes were very small and located in the lower middle area. So this creates a problem. So the model starts to assume weapons are always small and in the center. But in real life, weapons could appear anywhere in the image, like in the hands or somewhere in the image. So in someone's hand or on the ground or on the table. So we realized that our data needs to be more diverse, showing weapons in different places and sizes. So this is a model evaluation of detection example. So after training the model, we tested it on real world surveillance footage that it had never seen before. and it was able to correctly detect a weapon with 60% confidence, as we can see from the image, like the weapon 0.60. So that's a good sign, and it means the model was not just memorizing the training images, it actually learned how to identify a weapon in new unseen videos. So this shows that our model has the potential to be used in real-time systems for safety and security. So we started with a custom model, but it didn't perform well. So then we switched to YOLO V5, a smarter, faster model, and saw much better results. So our model was able to detect weapons with decent accuracy, especially given our small dataset. So we reached a peak F1 score of 0.40 and got a confidence sweet spot around 0.24. That I need to say that, and there is a still work to be done. The model misses many weapons. We need to improve the recall, and we need to collect more diverse training data and fine tune the model further. So overall, YOLO V5 has proven to be a great choice for real-time weapon detection at the student project level, I can say that. So the next thing we are gonna do is, first, we need to expand our dataset, collect more images with variety of weapons, sizes, and positions. And the second thing is we should work on balancing the number of weapon and non-weapon images. The third thing is we'll explore newer models like YOLO V8, that's the latest version of version 8 of YOLO, or transformer-based models for even better performance. So we also plan to test our system on real-time video streams instead of just images that we have done here on the update 2, and which will help us bring us closer to the real world use. Thank you.